Oops, let me adjust some lights. Okay, so last time we got partway through this particular lecture, and I just want to review a couple things before we move on, just to kind of prime the pump here. So we had introduced this concept of the Hertzsprung-Russell diagram, which is a tool that can be used to help us understand the relationship of stars in terms of their temperature and luminosity. It also contains information about the size of the stars and their spectral classes and their implications from the Hertzsprung-Russell diagram as far as the lifetimes of stars and where the stars are in that lifespan. When the stars are in the primes of their lives again, they lie along this diagonal swath called the main sequence. Okay, and then when they're aging, we talked about them evolving up to the giant or supergiant end of the upper right-hand side of the HR diagram, and then the bottom left is where you have your stellar corpses. Yeah, I'm sorry, I forgot to tell everyone, go ahead and get your clickers. Okay, and then this was just another example of an HR diagram where instead of having the stars different appear to be larger or something, you have all of the dots on here are the same size, even though in reality the ones in the upper left-hand corner we know are larger than the ones in the bottom right-hand corner along the main sequence. And of course these giants are also really large, whereas the white dwarfs are very small. Okay, and we went through these clicker questions, so don't feel the need to start clicking. We already went through these. We realized that this lining them up according to spectral class and seeing this nice neat pattern arise of their size relationship to one another relies upon the assumption that you are talking about stars on the main sequence, because otherwise if you're talking about a red giant star, it might be red just like this M star, but it's going to be bigger than possibly everything on here. And then we also talked about the fact that cool stars are possibly luminous if they're very large, because then they have more surface area to emit light. Okay, so that's where we left off last time. And so, you know, I talked about the size sort of loosely speaking here when we were talking about the radius of the stars, but there's another measure of the size of an object, and that's its mass, right? So we can look at how mass relates to luminosity as well. I've already said that the bigger the star, generally speaking, the more luminous it is, right? By bigger, I'm talking about radius in that sense. But it's also true that the more massive the star, the higher its luminosity as well, and that sort of makes sense. Generally speaking, if you're large in radius, you're probably going to be fairly massive as well, so there's a connection there. In fact, you know, the connection might stick out in your mind as being, well, stars are roughly spherical in shape, and if I assume the same density throughout the star, then, you know, the radius is just going to tell me something about, you know, the volume of a sphere would be 4/3 pi r cubed, and that's the radius that I'm plugging in there, and then I would multiply it by the density, and bam, I've got the mass. So clearly the radius and the mass are related to one another. It's not quite that simple, but because it's not the same density throughout, but nevertheless there is a relationship between mass and luminosity, similar to how there is a relationship between radius and luminosity. So on the horizontal axis of this graph, you've got the mass of a star plotted based upon masses of the sun. This subscript that looks like a circle with a dot inside of it is a common subscript that astronomers use to mean the sun. Okay, so 1 on here, 1 mass of the sun would be the sun's mass. Similarly, on the y-axis here, you've got luminosity as measured compared to luminosity of the sun. See the subscript there again with the circle with the dot inside, meaning the sun. So one luminosity here is one luminosity of the sun, meaning that's the same as the sun's luminosity. So if you go and find the horizontal coordinate corresponding to one solar mass and the vertical coordinate corresponding to one solar luminosity, and you find where they intersect, this is where our sun would lie along this line. Okay, so clearly there are many more massive stars and some less massive stars as well. And these are actual data points, and you see they fit very neatly onto this line of what you would get if you said that L equals exactly mass to the 3.5 power. So it's not precisely that, but it's pretty close to what we call a power law as physicists, where it's basically you take that and you raise it to a power, you take the x coordinate, you raise it to the power, and you get the y coordinate. And so that's what this line would be. Okay. The reason it looks like a line, because you might be thinking, well, wait a second, if I do x squared, that's like a parabola shape. I don't know if anybody's thinking about it this deeply, but you might be thinking, well, a line should just be x, not x to some power. So the reason that this turns out to be a line is because we've got a scale here on the y-axis that isn't linear, right? This is like 1 and then 10 and then 10 to the 2, right? So it's not like a 1-to-1 relationship here. So if you were to plot it slightly differently, where you had a 1-to-1 relationship, it would appear to be more of like a curve. Okay, but nevertheless, the point of the matter is that if you just blindly go with this equation that luminosity equals mass to the 3.5 power, you're going to get a pretty good estimate of what the luminosity of the star is if you know its mass, or if you know the luminosity, you could then figure out what its mass is pretty accurately. Okay. Speaking of masses, how do we know anything to verify this other than what I've just plotted there? Where do these values come from? A lot of what we know about stellar masses or stars' masses comes from the study of binary stars. It turns out that many stars, possibly the majority of stars even, do not come with just a star in that system. A lot of times, that star has a companion that is gravitationally bound to it. Sometimes more than one companion. When we talk about Alpha Centauri, our closest star system, there's actually 3 stars that are gravitationally associated with one another in that star system. But binary stars are fairly common, where you've got 2 stars. And the chances of those 2 stars being exactly the same mass is kind of small. It's kind of like, if you are you and your sibling, you wouldn't expect you to be the exact same height or weight, right? So these kind of sibling stars are not necessarily the same size, but they are gravitationally bound to one another. And so what's going to happen is that they're, in a sense, going to orbit one another, but really what's happening is they're orbiting what's called the center of mass. So if you've studied physics at all, you could think of this as the balancing point of say, a fulcrum, right? So you may have learned, if you took a physics class, that, a more massive object would have to sit closer to the fulcrum than a less massive object in order for them to balance one another. So the center of mass would be sort of like the fulcrum in that analogy. And so these stars are going to orbit around this fulcrum, which there's nothing really there physically. It's just where the center of their collective mass would be. Okay? And so what you would actually see of their orbits is something like this, maybe. Okay? So this is like a typical binary star situation. It's not always quite that nice and neat, but it's pretty typical. So as far as how we are able to detect a binary star, even if this is what's going on, how do we know that that's what's going on? Because remember that star systems or planetary systems out in space could be oriented in any number of ways. It's all sort of random chance. I could be looking, and the same is true of galaxies too, right? I could be looking at something where the galaxy is like flat like this, and I can see that it's like a nice spiral and here's the center. Or, you know, similar with a star system, I could be looking at it where it's flat and I see that, you know, here's the star and the planets orbit around it or something. Or it could just be that I'm looking at it edge on, maybe. And this is how I see this galaxy or this star system, and it's going this direction. Or it could be at any orientation in between. It's just however they're randomly distributed in space. So how am I going to be able to detect that something like this is what's happening? Because I don't necessarily have this bird's eye view of it, right? So there are a couple ways by which we can detect binary stars. Also, I should mention that it's very rare that I'm going to be able to see the space between these two stars, because even though they may be separated by a fairly large distance, chances are much, much farther away from that star system than they are from one another. So for me to actually tell that there are two separate stars there, it's not that common. So there are other ways by which we can figure this out. Now, if it does happen to be the case that they do separate nicely, and I can tell that there are two separate stars orbiting one another, and I can visually separate them and see that, then I call that a visual binary, right? Because I can visually see that there are two separate stars here orbiting one another. I mentioned an extrasolar planet HD 80606b when we were talking about seasons. And I think it was Eddie that asked, well, what if it was on a really elongated orbit instead of a nice neat circle? Would that give you seasons? And I said, yeah, you know, that would be the case. Well, that was a planet orbiting one of two stars that I was talking about. And those two stars, HD 80606 and HD 80607, actually do form a visual binary where you can see that there are two separate stars. Incidentally, that's why that planet's orbit is on such a funky path, is because there's a nearby star here that's gravitationally perturbing it, so it's on this extreme elongated oval path. But that's a tangent. In any case, the point is that sometimes you can see the separation between the two stars that are gravitationally associated with one another, in which case we call that a visual binary. Okay, but like I said, most of the time you're not going to be able to see that. The stars are just so far away that for you to see that there are two separate stars there is not going to be possible. So there's one of two other ways that we might be able to detect a binary star system. One way is through the Doppler shift in their spectrum, which I'll discuss in a minute, and that's called a spectroscopic binary. And the other, which is maybe a little bit more intuitive to discuss, is something called an eclipsing binary, where one actually crosses in front of the other to our line of sight. And that would be the situation. This eclipsing binary is only going to occur if you happen to be looking at the star system edge on, right? So that's like this. And so at some point during the orbit, let's say that my knuckle here is you know, one star, and then the other star is crossing in front of it. It's going to, I'm going to see that cross in front from my line of sight. And that's going to do something to the amount of starlight I actually detect. It will eclipse some of the starlight that I actually detect. And so even though I can't see the two stars separately, I see the light from the two stars changing on a periodic basis. And so that's how I know that that eclipsing is occurring. A spectroscopic binary, on the other hand, has to do with being able to detect the Doppler shift in the spectrum of the stars. And so you're looking more at their spectrum and seeing that wobble having a periodic basis to it, a red shift and then a blue shift, a red shift and then a blue shift, in which case you can tell that the star is wobbling in response to something. So here's maybe a little bit better description of what I mean by that. So let's say you can't really tell that there are two stars here, okay? But you can, with your telescope, measure the spectrum of what you're seeing is basically, you think, one star, okay? So here's the spectrum that you get, okay? Well, in actuality, there are actually two stars here, and as they are moving around the center of mass, there will be a period of time in their orbit where one of them might be moving towards you and the other one moving away from you. In which case that nice neat line that you first detected is going to be shifted, right? So this line that should be here has been shifted over to here and here. Okay, one due to one star and one due to another star, because this one is moving towards you, so it is blue shifted, and this star that's producing this line is moving away from you, so it's red shifted. Okay, so so you keep observing the star and you see, okay, well, it was nice neat spectrum, and now I seem to see a set of lines where one appears to be blue shifted and one appears to be red shifted. I keep watching it, and then it sort of collapses back into this initial spectrum that I got before, where everything was nice and neat and single lines in my spectrum. Well, that's because the stars have moved again, and they're neither moving towards you nor away from you. They're at a different point in their orbit where they're moving kind of sideways from your line of sight. So you won't detect any redshift or blue shift to either of these stars. If you keep watching the star, then you're going to see this pattern reversing, because now they're at a point in their orbit where instead of A moving towards you, A is now moving away from you. And instead of B moving away from you, B is now moving towards you. So you see that slightly thicker line, instead of being blue shifted, is now shifted in this direction, so it is red shifted, closer to the red end of the spectrum. Whereas this line that had been red shifted before is now blue shifted, indicating that it's moving towards you. And then you keep watching the star and you see the original spectrum that you saw before, and then the pattern continues to repeat. Okay, so from looking at the spectrum and seeing this pattern arise of nice neat spectrum, then some kind of red shift blue shift thing happening, then nice neat spectrum again, then some kind of red shift blue shift happening again, then nice neat spectrum again, and repeating that cycle on a predictable period, you can deduce, well, there must be something happening here to the star that I think I see as one star. The explanation that makes sense is that there's actually two stars there, and one at one point is moving towards me while the other's moving away, and that at a later point the reverse is true. And because this cycle keeps repeating, then that indicates there is some sort of predictable orbit of two stars orbiting a center of mass. And from that, we can sort of indirectly deduce that we're looking at actually a binary star system instead of one star, even though we can't visually separate them and see the two stars. Okay, it's kind of like indirect evidence. It's like the footprints that are left in the snow. They had to have been put there by something. And seeing these Doppler shift in the spectrum repeat itself in a periodic way is kind of like the footprints in the snow that, well, something had to produce this. And a binary star system is the best explanation. Okay? So does that make sense? It's a little bit complicated. It's a lot less intuitive than the eclipsing binary. Okay. So then getting back to the eclipsing binary, hopefully this will be something that's pretty straightforward for you to see. If you happen to be looking, like I said, at a star system edge on, where the whole orbital plane is aligned to you this way, and if you do draw a line straight up from that orbital plane perpendicular to it, then this would make exactly 90 degrees to your line of sight. Okay, and so if you happen to have a star system aligned that way, then what's going to happen is that at one point in the orbit, this star will cross in front of your eyeballs. And what it does when it does that is it's blocking out some of the starlight of the star behind it. Okay? And yes, it's still producing starlight of its own, but when it was over here, you were able to get starlight from both of them, right? So you were able to get the full starlight of both of them. But then once it's crossing in front of you, it's blocking out some of the starlight from the star behind, and so you're getting most of this starlight, but not all of it. Even though you might be getting all of this star's light, you're not getting all of this star's light, so it looks dimmer to you. Okay, and then if you can imagine continuing on this orbit, and at some point maybe this one would cross in front of your line of sight and you would have the opposite scenario. Okay, and so what you would see then, if this is taken over a time period throughout the star's orbit is maybe during most of the orbit you're getting, like I said, the full starlight from both of these stars. So your brightness that you're detecting is rather high. Then at some point this guy might cross in front of you, in front of this one behind it, and then it's going to block out some of the yellow starlight, and even though you may be getting all the red starlight, you're not getting all the yellow starlight, so you see a drop in your brightness. Okay, and so we call that drop an eclipse. This might be a little bit exaggerated here, but you get the picture, right? It's not going to be as bright here when this guy's covering up some of the starlight compared to what it is here when you're getting the starlight from both of them. Okay, and remember, you're not able to see that they're two separate things, so to you this looks like one big bright star. But at this point it's blocking some of that starlight out, so you're only getting a fraction of it. Continuing on, once they're, the eclipse is complete, then you're going to get the starlight from both of them again, so your brightness level will increase, and you'll have roughly the same brightness that you had originally. And then when this guy goes behind it, now suddenly you're not getting the starlight from the red star at all, so you get another eclipse taking place where you get less brightness here, less starlight here during that eclipse. And then when they separate again, you're kind of back to the original situation where you have the full brightness of both stars, and here the pattern is just repeating from this frame here, the second frame. Okay? So when you have these eclipses taking place where you see the starlight is a certain level of brightness, then suddenly it's dimmer, then it's bright again, then it's dimmer again, and this pattern repeats periodically, you can then deduce that something had to be going on to produce this. Again, you can use this as an indirect evidence, again, sort of like footprints in the snow. Something had to create this, and so a binary star is often the best explanation. By the way, both the spectroscopic binary star, just as a side note since we're not going to get to really study planets too much here, the spectroscopic binary detection technique and the eclipsing binary star detection technique can be used to find planets as well. Okay, because you could imagine, what if this was just a planet instead, right? Then, here it's going to block out some of the starlight. And then here it's not blocking out the starlight. It may not be giving off its own light, right? But here it's definitely blocking light out. And so, if you can detect that dimming, you can deduce that there are stars there. Likewise, with the spectroscopic binary, you may not get this secondary line, but you may see this, primary line from the star being shifted, blue and then red, and then blue and then red. The planet itself may not have its own line, but you'll still see that Doppler effect occurring. So both of these techniques have been adapted to detect planets that are orbiting other stars as well. Yes?
For the eclipsing one,
Mm-hmm.
you were saying you would see the stars from edge on. What does that mean? How does that work?
Well, it's sort of like random chance. If it happens to be aligned this way, where you just happen to be seeing it where the star system is like this and they're orbiting in this plane, then you might see an eclipsing binary. So, that kind of alludes to an important point. You won't see this for every binary star system, okay? You probably should see this in most cases to a certain extent, unless it's completely flat, and then, now it's never going to move towards you or away from you. But you won't always see this. This is only going to occur in roughly maybe 10% of binary star systems. Okay? Good question. All right. Oh, and the other thing is that because you can tell how much light is blocked out, you can kind of make an estimate then of how big the thing is in terms of its radius that's blocking out some of that light. So you can get a measure of the star's radius from using, if you happen to have an eclipsing binary star system, you can tell something about its radius. The spectroscopic binary system is going to tell you a lot about the combined mass of the star system, because depending on how dramatic this shift is, the more massive things are going to produce a more of a Doppler shift. Okay? So there's one other way that we can get a handle on a star's radius, And that is only going to be useful for relatively close by stars where we can actually resolve the size of the star with our telescope. And this is a little bit tricky to do and requires a technique called speckle interferometry, which we're not going to really go into great lengths to describe. But if you're able to use this technique and get some kind of resolution where you can get, rather than a pinpoint of light, you can get something that's roughly circular in size, then you can make some estimate of its actual radius relative to the size of the Earth's orbit and other things of that nature. And so what you're seeing here is the star Betelgeuse, which is in the constellation Orion. It's this upper left one here that's a red giant star. That makes it a little easier to get a resolution because it's giant, right? And so you're able to kind of get some picture like this, and through speckle interferometry get some sort of measure of its radius that way. But this kind of direct measure is not possible to do for every star. Okay, now going back to this Hertzsprung-Russell diagram again, hopefully now you see that we're not just basing these things on assumptions. There are ways that we can get a handle on the size of the star, and especially through studying binary star systems, all of that data is sort of there, and once we know the properties of a main sequence star or giant star, then if a star happens to fall at this point of the HR diagram, then I can just read off, well, its radius must be whatever's along this line, its luminosity must be whatever this is, etc., etc. Okay, and so there's another thing that I mentioned when we were doing the review about the fact that the HR diagram has implications for a star's lifespan, where it is on its lifespan. And so roughly speaking, we identified 3 regions of the HR diagram, one being the main sequence, which is probably the most important for the star for most of its life, is where it's going to live on the HR diagram. But then we identified 2 other spots on the HR diagram, the upper right-hand region being the giant end of its lifetime, near the end of its lifetime, and the bottom left being the stellar corpse region where the white dwarf stars live. And so what you can do is sort of piece these ideas together and see how a star would change if you followed it throughout its lifetime, and let's say that you could just plot it. Okay, at this epoch, this is where it is on the HR diagram. 1 billion years later, this is where it is on the HR diagram. 3 billion years later, this is where it is on the HR diagram. And if you would plot that progression through time, you would see that the stars evolve towards the ends of their lifetime, and they don't stay along the main sequence anymore, and they go to other regions of the HR diagram. So let's track the lifespan of a star like the Sun. So you see this sort of fuchsia colored, I don't know why they colored it fuchsia, because really when it's on the main sequence it's more yellowish. Nevertheless, that's what they used to indicate it here. That's our starting point. That's a star like the Sun. You see it lines up with 1 solar luminosity and about 6,000 degrees Kelvin, which is around the surface temperature of our Sun. Okay, so this is a star just like the Sun. After about 10 billion years or so on the main sequence, it's going to start to move off of the main sequence. And the reason, we'll talk about exactly why that's happening in a moment, but the reason that it's doing this, it's not staying along the main sequence, is because it's actually starting to run out of fuel to fuse. And perhaps counterintuitively, it actually gets brighter in this process. See, it's moving up in luminosity, but it's also cooling off in temperature, at least surface temperature anyway. And so it'll reach a phase here where it's gotten larger, it's bloated out in size, and it's more luminous. And then, you keep following it through this end period of its lifespan, and you'll see that it bloats up at a later stage even larger, more luminous, but also cooler in its surface temperature. This is like the very beginning of the end for the star. And ultimately, when it exhausts all its fuel, its outer layers are going to just shed away, okay? And that's what we call a planetary nebula. And then the glowing ember, so to speak, in the center is really small, and it will end up over here in the white dwarf region, and that will be all that's left behind. It's like the skeleton inside of the sun, not literally speaking, but it's like the ember after the fire dies. It's not really fusing anything anymore. It's just glowing hot, and it's really small. It's just a fraction of what it used to be. Okay, so in a nutshell, that's an overview of the later stages of a star like the sun. Strangely speaking, we always use the term evolution when we're talking about the end of stars' lifetimes. Usually evolution it conjures up to me something getting better and, new things happening. But for a star, when we say stellar evolution, we mean it's changing in the sense that it's aging and it's going to die in a short span of time, at least astronomically speaking. Okay, so that's in a nutshell what's going to happen to a star like the sun. Now, if we look at stars of all sizes that are on the HR diagram, it turns out that how long they spend on the main sequence is going to depend on where they are on the main sequence. These big, hot, luminous blue stars in the upper left-hand side are going to burn through their fuel much faster, as we discussed a little bit last time. And because they don't live as long on the main sequence, they're going to start to evolve off of the main sequence sooner than, say, stars that are like the sun, or stars that are red stars, which burn their fuel over a very long span of time indeed. So let's say that you could study a population of stars that were all quote-unquote born at the same time. Okay, so this is like a litter of puppies. They're all born at the same time. And unlike puppies, this is maybe a bad analogy because when it comes to stars, the runt of the litter is going to last the longest. And the biggest, fattest puppy is going to die off sooner. Okay, that's just a fact of life for stars. Clearly that's not always the case with puppies. But think of that in a very loose sense. They're all born at the same time. And if you know in advance that the larger ones are going to die off sooner, whereas the smaller ones are going to live longer, let's say that you just take a family portrait at one point in time of this litter of puppies, of these stars that were all born at the same time. If you see that, the bigger two of the litter are already aging and about to die, but all the rest are good, then you know, okay, well, this litter of puppies getting kind of old. The ones that I expect to die sooner are starting that process, but the ones that I expect to live longer are still doing great. They're in the primes of their lives. On the other hand, if you take a family portrait much later of the same litter of puppies, what are you going to see? Well, maybe those blue, bigger puppies are now already dead. You don't even see them at all. They're gone. They're dead and buried. So you have fewer puppies now. And now maybe some of the smaller ones are starting to age as well. And so now you know, well, it has been a long time since these puppies were born. This litter of puppies is no longer puppies, right? They're getting pretty geriatric at this point. So the analogy here is if you know of a cluster of stars that were all born at roughly the same time, then you can plot that cluster on an HR diagram and figure out how old the cluster is. Because if you see, let's say that these dots are what I actually see in the cluster, the yellow dots. The background dots are like what I would expect of a random sample of star. But these big yellow dots are the stars in my cluster. Okay, and in this family snapshot, I see that some of the bigger, bluer stars are starting to age. Some of them are even in their giant phase, but none have, ended up in the white dwarf phase yet, and all of these yellow stars and such are still in the primes of their lives. And in fact, these red stars are still, quote unquote, growing up. They haven't really even landed into adulthood on the main sequence yet. And so looking at this, I can tell, well, that's a relatively young cluster. Okay? But if I saw a similar cluster, okay, so here's another example of a really, really young cluster where no one has aged yet. And this is a young cluster where, still no one has aged, but everyone's reached adulthood. This is kind of like the one I had on the previous slide where some of the bluer ones are starting to age, so it's still relatively young. But if I look at a different cluster that may be older, I'm going to see that a lot of these stars are starting to age, even some of the yellow ones, and I don't get any blue ones at all. Maybe they're gone, they've died off entirely. And a really, really old cluster, you're going to have almost all the stars in the giant branch, and just the smaller, redder stars are going to still be in the main sequence because they live longer. Okay, so assuming that all the stars are born at the same time, all you need to do is plot them on the HR diagram, and automatically you've got an estimate for how old that cluster is. And the crucial piece of information you're going to look for to get that estimate is something called the turnoff point. Turnoff point is how far down the main sequence do I have to go before I get stars that I see, on the main sequence. This one, the turn-off point, where stars are starting to turn off of the main sequence, is not that far down. But in the bottom right, you see, I've got to go all the way down to near the bottom right to get to the turn-off point. So all of these stars are deceased, and these ones are aging, right? So the turn-off point is much, much lower and further to the right. And so this indicates a very old cluster. Does that logic make sense? Yes? That's a very good question. So you can't always assume this kind of thing, but what we call a cluster in terms of what seems to visually line up to us, and a cluster that's associated with one another are maybe two different things. So generally speaking, most stars, as we're going to see, are born in sort of a nursery, right? And they're all sort of born roughly around the same time. And oftentimes they stay gravitationally together. And that's what we really mean by a cluster. But if it just happens to be, a cluster that appears to be associated in space, it doesn't necessarily mean they are. You have to figure out, are they actually gravitationally associated with one another? And from there, then I'm safer to assume that they've been born at the same time. That's a really good question, though. Does that make sense? Okay. Other questions about this? Okay. So that's just kind of just to show you another usefulness of the HR diagram. This I don't think I'm going to dwell on a whole lot, but it turns out that during some periods of some stars' lifetime, they're going to go through a period of variability. By variability, I just mean that their luminosity is not going to be stable. You're not going to be able to say, it's this many watts. The brightness of the star itself will fluctuate or vary, so to speak. And how that varies depends on what kind of variable star it is. But generally speaking, if a star happens to lie along this little strip here that almost makes like an X with the main sequence, we call that the instability strip. And if it lies along that strip, chances are that its luminosity is going to be unstable and it's going to vary in some way. Obviously, there are a couple here indicated that are outside of the instability strip that are also variable, the Mira variable stars, but most of them are going to lie along this instability strip. There's not really a physical explanation for why that's an unstable region. It just, there is, it's just a little bit more complicated than we need to get into. But just suffice to say, if we happen to see, a star lies right here, then I can kind of know, well, that must be some kind of Cepheid variable star or RR Lyrae star. Okay, so what do I mean about how its luminosity can vary? Well, I mean basically what it sounds like. I mean that it's going to look brighter at one point than it is during another point. Okay, so for example, take this image and look at this reddish star here, and then compare it to over here, and you see that it's gotten a lot brighter. Okay, now this, you may wonder, well, how can I then tell if this is some kind of eclipsing binary star rather than a star which is just inherently variable? And there's a couple answers to that. One is that most of these variable stars have predictable periods. Okay, so if it varies on a period that fits with a Cepheid or an RR Lyrae variable, then I might want to reconsider whether I think that's a binary star producing an eclipse or if it's just a variable star. And the other thing is that if its position on the HR diagram is along this instability strip, then I can pretty much assume it's probably due to it being inherently a variable star. Okay, so this is an example of a variable star where you might look one night and it's a certain brightness, and you look another night and it's a different brightness. Okay, and depending on the type of variable star, there's a relationship between its inherent luminosity and how quickly its luminosity changes. So you see here on this graph that along the horizontal axis you have how long of a span of time is one pulsation period. For it to go from bright to dim back to bright again, how long does that take? That's what our period is along the horizontal axis. Along the vertical axis, this is what its inherent luminosity is on average, right? So what is its average inherent luminosity? Okay, and it turns out that how fast it's pulsating is going to have to do with its inherent luminosity. If you're an RR Lyrae star, you kind of make this little horizontal line here, and your pulsation rate is usually a matter of a couple days, and your luminosity is usually a steady point right here just below 100 solar luminosities. And if you're a Cepheid variable star, then if you only vary over a few days, you may be this luminous, not very luminous. But if you vary over, say, 100 days, then you're a much more luminous star. So notice that I keep using the word luminosity here. Okay, why might it be useful? Think about it from an astronomer's perspective. I'm looking at a change of brightness, and I detect that change of brightness, maybe let's say that I look at a star and I see that its change of brightness is 2 weeks. Okay? And so from this period luminosity relation, I know that it's got to be this luminous. Just by measuring the change of brightness, I can tell how luminous it is based on its period of change of brightness. So why might this be useful? Can you think of a situation in which that might be useful? Why would it be useful to know the star's luminosity? Okay, let me try to lead you through the logic a little bit further. I can tell its brightness, okay, but I don't necessarily know its luminosity until I've been able to measure this period, and then I say, well, from that period I know it's such and such luminosity, and I also know that it's this level of brightness. What can I figure out if it's supposed to be this luminous, but it's this bright to me? Exactly. You can tell how far away it must be, right? Because if I measure its brightness and I say, okay, it looks like it's this bright, but based on this period luminosity relationship, I know it really should be this luminous, Now I can work backwards and say, well, it must be so and so light years away for it to appear only this bright to me. And I can work out what that distance is. Very good. Okay. And so, yes, that's what I'm getting at here, is this relationship to brightness and luminosity and distance, that those three things are related. If I get a measure of brightness, and now I've been able to deduce what the luminosity is based on this equation, then I can solve for distance. Okay, and that has to do with the inverse square law of light. Anytime I have something, an object, usually it's a star, that is very standard in its luminosity, and then I can make assumptions that, well, based on some other factor that I observe, it has to be this luminous, and thus I can work out the distance. We call that a standard candle. Okay, it's sort of silly. I don't know why candle is used, because clearly stars are not candles. But if you could think of it like all these candles are always this amount of wattage, then I can know that if it's only this bright to me, then I can work out the distance. So anything that helps you work out the distance based on some standard known luminosity trait is something we call a standard candle. Variable stars are an example of a standard candle that help us determine the distances that these stars are away. Okay, and I guess that's the end of this lecture. Let me hit a pause here. I guess we didn't actually need our clickers quite yet.